Hello everyone, welcome to another video. And for this video, we will talk about alpha, beta, unsaturated carbonyl compounds and their reactivity towards nucleophiles. So you have seen the structure. This is what we call an alpha, beta, unsaturated carbonyl. Why alpha, beta? Because there is a degree of unsaturation sa alpha and beta carbons. So we all know that an alpha carbon siya ang carbon next carbonyl compound. So this is the carbonyl here, C double bond O. This is the alpha and this is the beta. That is why it's called alpha beta unsaturated carbonyl compound. So various nucleophiles could react to this carbonyl compound. Okay, so duha ka about klase ang mechanism. Number one is that kung ang nucleophile mo attack siya here, mo attack siya dere, this process would now be called a 1,4 conjugate addition. Why 1,4? 1,4 because this is 1, 2, 3, and 4. That's why 1,4. No, not that one. 1, 2, 3, 4. Okay, upon this process, kung ma-attack this nucleophile, there is an intermediate gamma form here. So basically, the intermediate would look like this, because this pi electrons will shift towards here, and this will flow towards oxygen, since oxygen is an electronegative atom, then carbon. So one intermediate. Sorry. Okay. So ang mahitabo is kani siyang intermediate. This is what we call an enolate. Okay. Ang mahitabo is that kaning lone pair ni oxygen would go here, and then this pi electrons will be shifted towards this carbon to form this species here. And this one is a carbanion. That is very nucleophilic and could abstract a proton or any other nucleophile could abstract. And so, for example, there is a proton here. It could abstract it and will form the product. Here. So that basically is the mechanism when you have 1,4 conjugate addition. But lahi kung na kay nucleophile nga mo attack sa carbonyl directly. This is kung inanigali ang process, ang tawag ana siya is 1,2 direct addition. This is 1,2. Okay, so notable is that the nucleophile will attack directly to the carbonyl. Same gyapon nga process. So that the intermediate would be So this is the intermediate, and this intermediate is what we call a tetrahedral, and not an enolate intermediate, but a tetrahedral one. And dimethyl it's either um, an addition reaction, and this oxygen would just abstract a positively charged species around, or substitution when there is a good living group. For example, this R here, this R is a living group, then these electrons from oxygen would shift towards the carbon and pull out this R, assuming na ang R kay living group. So that is a substitution, depending upon the condition as well. So inani ang two possible ways nga mo react ang nucleophile sa alpha beta unsaturated carbonyl compound. But unsa man mo pagkabalo nga ang nucleophile, kung kano sa ang nucleophile mo attack sa double bond ba, sa carbon-carbon double bond ba, or sa carbonyl? So to answer that question, kinahanglan tag understanding about Pearson's hard soft acid base principle, or the HSAB principle. And HSAB principle, it's just pareho siya sa like dissolves like hard bases react with hard acids and soft bases react with soft acids. And in organic reactions, hard nucleophiles would love to react with hard electrophiles, and soft nucleophiles would love to react with soft electrophiles. Okay. So, unsa man yung mga hard nucleophiles and hard electrophiles? Saan yung pagkabalo? By the way, before we go over that, ang kaniyang hard soft acid principle, acid base principle, is particularly a description for Lewis acids and bases. Okay, Lewis acid base siya na species, or acid or base. The hardness, when you say hardness or softness, so sa Lewis acid or Lewis base, this is independent of strength. Strength sa Lewis acid or Lewis base. Dili siya mag-matter kung about the pKa of the Lewis acid or the pKa or the pKb of the Lewis base. Na other factor na mo-affect sa hardness and softness, or mag-determine sa hardness or softness sa Lewis acid or base. Okay. Number one is that ang pinaka-main Gino principle is what we call polarizability. This is the main effect here. Polarizability. Okay. Si kaning hard nucleophiles and hard electrophiles, they have low polarizability. Whereas ang soft species, they have high polarizability. And take note that polarizability is akin to ionic. Oh, no, not ionic, but the atomic radius or atomic radii sa isa ka atom. The bigger the atom is, the more polarizable, the more easy can it be polarized. Okay, so another difference is that hard nucleophiles and hard electrophiles, since they are low, they have low polarizability, they are smaller in terms of size, while soft species are bigger in size. And mostly this hard interaction, this hard interaction, ang pinaka-governing principle or governing effect is the electrostatics. Mostly ionic interaction. Okay. Whereas kaning soft species, mostly is the covalent bonding or the molecular orbital overlap. Okay. Hard interaction are mostly charges, and soft interaction are mostly governed by orbitals, particularly molecular orbitals. Okay. So there are before kumantan today, let us focus first on what polarizability is. Okay, the lower the polarizability, the smaller the compound is. The higher the polarizability, the bigger. The smaller the atom is, the low its polarizability is, and the bigger the atom is, the higher is its polarizability. So on some main concept polarizability, polarizability, this is just the tendency of electron clouds sa atom na distort siya by a nearby positively charged species or cation. As simple as that. Okay. So to understand this, I will have an example here. Suppose you have an atom like this and another bigger atom. Okay, small one and the big one. Of course, every atom has its own nucleus. And this one has a bigger nucleus because it contains has greater electrons, of course, and it's bigger. So we all know that the electron cloud, every atom has an electron cloud, and the electrons are like described as occupying some energy levels. For example, the smaller atom here, this is n equals 1. So now siya sa first energy level, and naa kay electron here. And we all know that the nucleus has positive charged particles, which we call protons. Our tendency is kaning electrons here will easily get attracted, like strong attraction towards the nucleus. Sorry. It's a very strong attraction towards the nucleus here. So on the other hand, kaning dako nga atom, of course na siya nucleus, which contains positive protons. So since dako siya ng atom, we assume na siya duha. For example, na siya duha ka na up to the second energy level ang gi-occupy sa iyang electrons here. For example, you have electrons here, electrons there, the local electrons, and then you also have another electrons in the outside, or the valence electrons. Ang metabo is ang kaning nucleus, kaning electrons, mga inner electrons, are easily attracted towards the nucleus, and strong ang ilahang attraction. Attraction. But for in the case of outer electrons or the valence electrons, weak ang ilang attraction towards the nucleus. Kaya layo kay sila sa nucleus. I-compare nimo diri sa small na atom wherein ang electron, even though i-assume natin siya na valence electron still incomparably greater ang attraction towards the nucleus sa smaller atom compared sa bigger atom. So that is why when you have a cation here, dali lang yung ma-distort ng electron cloud. because these valence electrons would tend to get attracted towards the cation. If we visualize this, for example, this is a cation. Okay, and you have this compound, which is a bigger compound, high polarizability. When they get attracted to each other, okay, ang labas ani nila is that there will be a distortion, because remember that this is positive and this is the electron cloud, or the valence electrons are negatively charged, of course. My tabo is that there will be a distortion of electron clouds. Na-distort ang electron cloud ni bigger atom, because its valence electrons are attracted more towards the cation instead of being attracted towards the nucleus, which is at the center. So that is what we call polarizability. The ease at which the valence electrons of an atom are easily distorted by an opposite charge. So we're talking about hard nucleophiles and hard electrophiles. So these are examples of hard nucleophiles: the hydroxide, the alkoxide, and these halogens, and also an alcohol, ammonia, acetate, carbonate, okay, and also organolithium and organomagnesium, which is a Grignard reagent. And hard electrophiles have examples of hard electrophiles are proton and hydronium ion and all these metals here, as well as the tertiary carbocation and the boron trifluoride, and of course the ketone, the carbonyl compound. Okay, in terms of homolumo interaction, which is an advanced organic chemistry concept, hard nucleophiles actually are, when we speak of homolumo interaction, it is actually their it's the homo of the hard nucleophile that gets attracted towards the LUMO of the hard electrophile. Okay, highest occupied molecular orbital interacts with the lowest unoccupied molecular orbital. This is filled and this is unfilled with electrons. And when we construct the orbital energy diagram, it actually looks like this. Kind of looks like this. This is the energy. If this is the hard nucleophile, HOMO, okay, and this is the hard electrophile, this is the hard nucleophile, HOMO, this is the hard electrophile, LUMO. This is the energy gap between them. Mas dako ang energy gap. That's because of their low, that is attributed to the low polarizability of these two species. Okay, so you have a energy release here. Dako ang energy gap. Okay. So this is in terms of orbital energy diagram. In contrast, soft nucleophiles and soft electrophiles are those that are neutral but sometimes charged, but they are bigger in terms of size, of course. And examples of soft nucleophiles are this: the thiol, the thiolate, the trialkyl phosphine, the iodide ion, which is of course a big halogen, and the phenyl, okay, and also the vinyl and organocuprate or organocopper reagents. Examples of soft electrophiles are this transition metals, okay, and borane, and of course the alkene moiety of the alpha beta unsaturated carbonyl, and of course the CX bond in an alkyl halide, specifically the tertiary carboxyl ion in an alkyl halide. That's a soft electrophile. Okay, so the same concept of homo-LUMO interaction. The HOMO of the soft nucleophile interacts with the lowest unoccupied molecular orbital of the soft electrophile. But the difference is that if we write the orbital energy diagram here, we all know that this is the H, the hard acid HOMO, and this is the hard nucleophile HOMO and the hard electrophile LUMO. But in terms of soft-soft interaction, the energy release is small, or the energy gap is really small. Let me show. So this is the soft nucleophile HOMO, and this is the soft electrophile LUMO. So the energy gap is small compared kung i-compare nimo sa hard interaction. Energy released. Okay, so that is attributed to the very large, big size of the atoms of the molecule as a whole, of the soft nucleophiles and soft electrophiles. That's why it's very easy to fill a LUMO from the HOMO of a nucleophile. It's very easy because of the polarizability. Munang gamay ra kayo ang ilahang energy gap. Okay, so mabalik ta dire. When you have a nucleophile here, basically ang nucleophile is a soft nucleophile. Of course, it will attack here because this unsaturated bond here is a soft electrophile. And ang governing principle ani would be the molecular orbital overlap. These are the pi star molecular orbital here, unfilled, because you have the HOMO of the nucleophile gets donates an electron to the LUMO of the carbon-carbon double bond. And in molecular orbital concept, if we draw the p atomic orbitals, here, so this one is, of course, we all know that this is the pi star orbital. This is the LUMO, lowest unoccupied molecular orbital. There's no electron here because, as you can see, the phasing is not exact. Like, there's no phasing here. That's why there's a node, a region wherein you have no electrons. But in this case, the pi orbital here, there is phasing. So therefore, there is electron in between in this region. The probability of finding the electron anywhere in the middle or around here is great. So this pi orbital is the HOMO. And of course, you have a nucleophile that has a highest occupied molecular orbital that donates electron. Actually donating an electron to the pi star because it has no electron. So that is the molecular orbital concept in soft-soft interaction. Okay. Mostly molecular orbital gidang soft-soft. But if you have a nucleophile, a hard nucleophile, this will be the carbonyl itself is a hard electrophile carbonyl, because mostly governing principle on hard electrophile is that you have a electronegative element. Okay. And carbon versus oxygen, oxygen is the most electronegative. That's why it does minus, partially negative, and partial positive charges here. And most nucleophiles here, for example, hydroxide ion, this is a charged nucleophile. It's mostly interaction of attraction of electrostatic attraction of the charges of the hydroxyl to the partially positive carbon, electrophilic carbon rather. But of course, we cannot denounce the concept of orbital overlap rather for the carbonyl. And carbonyl rather, by the way, has the same molecular orbitals with the carbon-carbon double bond. So C double bond O, it has two molecular orbitals as well. Like example, you have this. Okay, there are actually p orbitals here in the carbon and the oxygen that overlaps to make a pi molecular orbital. And same siya sa alkene, carbon-carbon double bond. This is the pi, the HOMO, and this is the pi star, LUMO. Okay, but what happens if we do it as an in molecular orbital is that lobe sa carbon is bigger. Like for example, here. Bigger ang iyang lobe as compared there is oxygen here. Kasi naniman siya ang interaction, orbital description. Okay, that is why and of course the hydroxyl n orbital and molecular orbital will tend to overlap. For example, here. An orbital overlap, but actually more dominant electrostatic attraction, statics, when you have hard interaction. But take note, you cannot denounce the concept of orbital overlap, molecular orbital overlap in hard interaction, but more dominant lang jud ang charge when it comes to hard interaction. But in the soft interaction, less dominant or less pronounced ang electrostatic attraction, but more pronounced ang molecular orbital overlap. So that's the difference between hard interaction and soft interaction. So that is why when you have this unsaturated carbonyl compound, and if you have a Grignard reagent, for example, the reaction would be towards the carbonyl because the Grignard reagent is a hard nucleophile. Okay, but in the case of the organocopper reagents here, the attack of the nucleophile would be towards the carbon-carbon double bond and form the enolate intermediate. Okay. So because the organocopper reagents are soft nucleophiles, and this is a soft electrophile, and this one is a hard electrophile. So, na siya pag-predict kung asa mo attack ang nucleophile. It depends upon the nucleophile itself, kung hard nucleophile ba siya or soft nucleophile. And of course, you should know where is the soft site and the hard site in an alpha beta unsaturated carbonyl compound. So next time when you do reactions or mechanisms, always watch out for, always evaluate the nucleophile. If it's a hard acid, a hard nucleophile, it would react to the carbonyl. And if it's a soft nucleophile, it would react to the alkene.